Hello everyone. As I promised, we are going to go through a few sections that we skipped during the class. So in this video, we are going to go through section 4.7 maxima minima problems. Okay, so this is similar to what we learned in Calc 1, where you find the derivative to find the critical points, and using the second derivative test, you check whether it is a maximum or minimum. So this is kind of like the analog of that. Right. So first, a critical point. So let Z equals fxy is defined on an open set containing the special point x0, y0. That point is said to be a critical point if either both its partial derivatives are 0, or at least one of the partial derivatives does not exist. Okay, so the way to find critical points is you find its partial derivatives and check whether check the places where it does not exist. So those are critical points. Then make both of them equal to 0 and find x0, y0. So you have to do both. Now let's look at an example. Example number 38 from the book. Find critical points of this function fxy. It's a polynomial. So let's find its partial derivatives. Differentiate with respect to x, you get 2x plus 2y plus 4. Right? Then partial derivative with respect to y is 2x minus 8y minus 6. Okay, now even though we talked about two ways to find critical points, now these are defined everywhere. So both are defined over R2. Therefore, there will be no places where partial derivatives are undefined. So the only way we can find critical points are making them equal to 0. So you make fx equals 0 and f sub y equals 0. So we get two equations, right? You get two simultaneous equations and we have to solve them. So 2x plus 2y plus 4 equals 0. 2x minus 8y minus 6 equals 0. Okay, you can solve for x and y. You can use elimination method, substitution method. You will get x equals -1 and y equals, it's also -1. Okay, now that means we only have one critical point. So this is the unique critical point. The function has only one critical point, which is -1 comma -1. Okay, so that's the way to find critical points. Right, now this is part A of the example. Let's go to part B. So we have a much complicated function and we are asked to find the critical point. So the idea is similar to what we did here previously. Find the partial derivatives with respect to x and with respect to y. Okay, so with respect to x, now it is you will have to use the chain rule where this is the 1/3 power. So when you find the derivative, it will be 1/3 this whole thing, 4y squared minus 9x squared plus 24y plus 36x plus 36 raised to the power. So we are using the power rule. So 1/3 minus 1, negative 2/3. So in the denominator you have this term. On the numerator you have the derivative of the inside with respect to x. So it's negative 18x plus 36x. Now similarly, you can find partial derivative with respect to y, and the denominator will be the same. The numerator will be the derivative of the inside with respect to y. It's 8y plus 24. So we found gx and gy. Okay, now we have to consider, remember, we have two different cases. Okay, let's first check gx equals 0 and gy equals 0. The places where the partial derivatives are equal to 0. Now, to make them equal to 0, the numerator needs to be 0. So, we get a negative 18x plus, okay, I think there should not be an x here, plus 36 equals 0. From the second one, you get 8y plus 24 equals 0. And using that, you get x equals 2 and y equals negative 3. Okay, so that is a critical point. That is the only critical point we found by making the partial derivatives equal to 0. So 2 comma negative 3 is a critical point. Okay, now remember there was two ways to do this, by making them equal to 0 and then checking the places where the partial derivatives are undefined. Okay, now let's look at the partial derivatives. Now they are fractions. Now fractions can be undefined if the denominator is 0. Now both of them have the same denominator. So gx comma gy are undefined if the denominator is equal to 0, which means 4y squared minus 9x squared plus 24y plus 36x plus 36 equals 0. So the points that satisfies this equation are also critical points. Okay, so we can complete squares. So collect the y terms, 4y squared plus 6y. Collect x terms, negative 9x squared minus 4x plus 36 equals 0. Now complete square, you will get 4y plus 3 squared minus 9 times x minus 2 squared equals to negative 36. So complete the square and simplify the constants, you should get negative 36. Okay, now to make it look like an equation we already know, let's divide by negative 36. So I'm going to move things around. X minus 2 squared over 2 squared minus y plus 3 squared over 3 squared equals 1. Now we know what this equation represents. It's a hyperbola. So this is a hyperbola with center 2 comma negative 3, with center 2 comma negative 3. So that is the critical point we found earlier. Now all the points on this hyperbola are critical. So all points on this hyperbola are critical. In a sense, there are infinitely many critical points. Since the hyperbola contains infinitely many points, there are infinitely many critical points for this second example. Right. Now, the reason to find critical points is to identify a maximum, minimum, or extreme points, or local extreme points. Now, think about this function. So this is a surface representing a function with two variables. Now, these 2 points, so they are the peaks, right? They are called local maximum. Local maxima. So these peaks have the property that in the nearby vicinity, it's the maximum. So they are called local maxima. And the biggest out of them, in this picture, it's this one, that is the global maximum. That is the global maximum. Okay, and similarly, these 2 points are called local minima, and the smallest out of them, so in this particular picture, this is the smallest of them, that is the global minimum. Now, all these points are called local extrema, either local minimum or local maximum. So they are called local extrema. Now, if we have an interior point x0, y0, with the partial derivatives, having the partial derivatives f sub x and f sub y, then that point is a local extremum, implies that point is a critical point. Now what this does is, to find local extremum, you should start by looking for critical points, because all the local extrema are critical points. Now there are other types of critical points. So what this says is all the local extrema are critical points, but it's not the other way around. There are critical points which are not local extrema. There are critical points which are not maximum and neither minimum. So they are called saddle points. Critical points which a critical point which is not local extremum is called a saddle point. Now what this is as the name suggests, so saddle, think about the saddle of a horse. So the picture will be something like this. So let's say this is the x direction. From x direction, you see there is a minimum at this place. From the y direction, it has a maximum. So this is the picture. So it kind of looks like a saddle. So this point is the actual saddle point. At that point, so that point is a critical point, but it is neither a maximum nor a minimum. Now, okay, the question is, you can find all the critical points. How can you know whether it is a maximum or it's a minimum or it's a saddle point? The technique is the second derivative test. Now, in contrast to what we learned in Calc 1, this is little bit lengthier because it has more options. Okay, so let's go to it. Consider the function fxy, where its first and second order partial derivatives are continuous. So all the first and second order partial derivatives are continuous. And suppose the partial derivatives are equal to 0 at this point x0, y0. That means x0, y0 is a critical point. Now we define discriminant to be what we have here. This is the discriminant. The discriminant is first you find the second order partial derivative f sub xx times f sub yy minus the square of f sub xy. Now the conditions are, if the discriminant is positive and f sub xx, so second order partial derivative with respect to x is positive, then we can say, then the point is a local maximum. If the discriminant is positive and the second order partial derivative is negative, it's a local minimum. And if the discriminant is negative, then it is a saddle point. If the discriminant is equal to 0, the test is useless or inconclusive. I would say the test is inconclusive. So the strategy is you find all the critical points by making the partial derivatives equal to 0. So we don't care about the places where the derivative is undefined. So only consider the cases where both derivatives are equal to 0. So you found all the critical points, then you find the discriminant at that point and check these 4 conditions. Which one does it fall into? Okay, so let's do an example. Example number 39. Find local extrema using second derivative test. So find all the local extrema of this function f is 4x squared plus 9y squared plus 8x minus 36y plus 24. Okay, so the drill is first find the critical points. To find that, you have to find the partial derivatives. Partial derivative with respect to x is 8x plus 8. With respect to y is 18y minus 36. Okay, so in this case, you only have critical points. You don't have critical points where the partial derivatives are undefined because both are defined over R2. The only way to find critical points are you make them equal to 0. By making them equal to 0, you get, you can find x equals -1 and y equals 2. So that is the critical point. So let's write it down. -1 comma 2 is the only critical point. Is the only critical point. Now we need to check the discriminant. Right? So to find discriminant, we need partial derivative, second order partial derivative with respect to x, partial derivative with respect to y, and the mixed partial derivative. So you differentiate fx again, you get 8. To find f sub y, differentiate fy with respect to y, and mixed partial is 0. So this gives you the discriminant is the product of these two. So 8 times 18 minus 0 squared. Okay, which is a positive number. Right. Now the discriminant is positive and the partial derivative, second order partial derivative with respect to x is also positive. So now because of these two, let's go back to the second derivative test. Discriminant is positive and the second order partial derivative is also positive. That means it is a local maximum. Therefore, -1 comma 2 is a local maximum. Right. Okay, so let's do one more example. Again, what we are going to do is find all critical points by making partial derivatives equal to 0 and then find the discriminant. Partial derivative with respect to x is x squared plus 2y minus 6. Partial derivative with respect to y is 2y plus 2x minus 3. Now, okay, both are defined on R2. So the way to find critical points are, you make them equal to 0. So you get x squared plus 2y minus 6 equal to 0 and 2y plus 2x 3 equal to 0. Now we can eliminate 2y just by subtracting them. You get squared minus 2x minus 3 equal to 0, which can be factored is negative 3 and positive 1. So you get two answers, x equals 3 or x equals negative 1. So plug it back into the previous equation and you should get y equals, so when x equals 3, you get y equals negative 3 halves. When x equals negative 1, you get y equals 5 halves. Right, so that means we found two critical points. So there are two critical points. One is 3 comma negative 3 halves. And the second one is negative 1 comma 5 halves. Okay. Now we found critical points. We have to find the discriminant. So let's find double derivatives. This is 2x, 2, and the mixed partial is again 2. So therefore the discriminant is 2x times 2 minus 2 squared. So it's 4x minus 1. Now we have 2 points to consider and 4. Okay, so let me write them down. So gxx is 2x and d is 4x minus 1. I have two critical points. Let's apply each of these for each of these points. So for the first point, which says x is 3, so gxx is positive and d is positive. That means that point is a local maximum. Okay, so let me go back to the actual theorem and double check it. Yes, d positive double derivative positive, it's a local maximum. That is a local maximum. For the other point, for the second point, negative 1 comma 5 halves, gxx is a negative number. Okay, as soon as we, so the discriminant is plug negative 1, again you get c negative. So if the discriminant is negative, we get a saddle point. Right. So this is the drill. You find critical points, then you find the discriminant and compare it with the 4 different cases that we had for the second derivative test. Right. Now we talked about local minimum and local maximums. Now we are going to talk about absolute minimum, absolute maximum, or the global minimum and global maximum. Now, the way to find the absolute maxima or minima is you find all the critical points and the boundary points. Let the function fxy be a differentiable function on a closed bounded set. Then it has a global maximum and a global minimum. It will be at a place where either a critical point or a boundary point. We use partial d to indicate the boundary. So to find the global maximum minimum, what you do is you find all the critical points, you find all the boundary points, and find the function values at each of these points. Then the maximum value will be the global maximum, and the minimum value will be the global minimum. Now we will do an example. This is the last example we will do for this section, but it is a little lengthier, so I have dedicated 2 pages for that example. So let's go through it. Find absolute extrema of this function on this region. Okay, the region is x is in between 0 and 4, y is in between 0 and 2. So this is the region, a rectangular region. Okay, first let's find the critical points. So first thing, critical points. We know how to do this. Right? Find partial derivatives. 2x minus 2y minus 4. With respect to y, it's negative 2x plus 8y minus 2. You make them equal to 0. You make the partial derivatives equal to 0 and you simplify. And you should get x equals 3 and y equals 1. So solve these 2 system of linear equations and you should get a single unique solution, x equals 3 and y equals 1. So the critical point is 3, 1, and actually you need to check whether it is in the region we are interested in. Yes, 3, 1 is somewhere here. So it is in the region. That is a point that we are interested in. So let's find the function value at 3 comma 1. So let me write it down. 3 comma 1 is the only critical point, and the function value at that point is, you plug x equals 3, y equals 1, you should get 17. Okay, so we found the critical point and the value at that critical point. Okay, now I need to worry about, so we took care of the critical points. Now we need to worry about the boundary. Now this particular example has 4 lines as the boundary. So let me label them. So I'm redrawing the region. Let's say this is L1, this line segment, L2, L3, and L4. So what I'm going to do is, I'm going to parameterize each of these lines and then try to find the function values. Okay, so now after critical points, we are going to take care of the boundary points. First, let's take care of L1. Now remember, this is 0, 0, 4, 0, 4, 2, and 0, 2. Now to get L1, that means you plug x equals 0 and y is in between 0 and 2. So go back to your original equation. So the equation on the top, plug x equals 0 and you should get, so f of 0 comma y is 4y squared minus 2y plus 24. Now what this means is, on the line segment L1, the function is that, right? Okay, now we need to figure out the maximum values. So this is now reduced to a function with one variable. The technique is, you find the derivative. It's 8 minus 2, make it equal to 0, you get y equals quarter. Okay, so that means the critical point is 0 comma quarter. On that line, this point is a critical point. The function value is, you plug the function, you should get 23.75. Okay, now we need to find the maximum minimum for a line segment. You need to take care of the boundaries also. So these two values. Now let's find out these values also. The boundary points are f0, 0. You plug 0, 0, you get 24. Then you plug f0, 2, you get 36. So I'm not going to show how you get all these numbers. You just plug them into the function, you get the answer. Right. Now, okay, so we had the 3 comma 1 critical point here. Then on the line segment L1 we found 3 special points. Now all these points that I am looking for are the candidates for the global maximum and the global minimum. So we are done with L1. Now let's move to L2, line segment L2. So let me copy this picture down here. Right. I want to parameterize L2. The special thing here is now the y value is 2, x is in between 0 and 4. Okay. Now plug this into the function. So f of x comma 2 is, you plug and you simplify, you should get x squared minus 8x plus 36. Now find its derivative. 2x minus 6, 2x minus 8, make it equal to 0, you get x equals 4. Right? Therefore, the critical point here is 4 comma 2. Okay, so that is the other border. Now on L2 there is no critical point in the interior. The only critical point is in the border. So we have to find the function value of that point. At 4 comma 2 you get 20. Right. Okay, so we are done with L1 and L2. Now we are moving to L3. Okay, L3. It's again a vertical line, meaning x value is fixed. It's 4. Y is in between 0 and 2. Plug this x equals 4 to the function and simplify. You should get 4y squared minus 10y plus 24. To find, I forgot to mark that point. So to find the maximum or minimum, you find the derivative, minus 10, make them equal to 0, and you get y equals 5 over 4. So the point is 4 comma 5 over 4. X value is 4. 5 over 4 is a little bit more than 1. So somewhere here. The function value, you can calculate it. You should get 27.75. Right, so we are done with L3. Actually, we are not done with L3 because we have to take care of the boundary here. So 4 comma 0. Function value at 4 comma 0 is, plug it, and you should get 24. Okay, now we are done with L3. Let's deal with L4. it is a horizontal line. Where the y value is 0 and x is in between 0 and 4. Plug y equals 0 to the function and we should get x squared minus 4x plus 24. To find the critical points, you find the derivative, make it equal to 0, get x equals 2. So the critical point is 2, 0. In the picture it is here, middle. The function value at 2, 0 is, you plug it and you get 20. Now we are done with all the critical points and special point on the boundary. Now we found the function values of each of these points. So let me draw a summary here. So let me copy this picture. Now I'm going to, okay, so let's write down the values. At 2, 0, it's 20. At 4, 0, it's 24. 4, 5 over 2, 27.75. Likewise, I'm going to fill all these points with the function values we found earlier. So this was a 20, this was a 36, 23.75, 0 was at 24, and the middle critical point was 17. Okay, so out of these you pick the largest, that will be the maximum, global maximum. So 36, this point is the global maximum, this point is the global minimum. So global maximum is at 0, 2. The maximum value of the function is 36. Global minimum is at the critical point, so it's 3, 1, and the minimum of the function is 17. Okay, that is the end of this section, and I will upload another video for the next section 4.7.